Sir, we are live now.
Okay, so can we start?
Sir.
Amitesh, can we start?
Yes, sir.
Okay, so a very good afternoon to all of you. First of all, I'm very sorry. I'm extremely sorry for the delay. And yesterday I was very busy, some work, and therefore I was not able to send my PPT. But I promise I will send after this lecture to Mr. Amitesh so that you can get the PPT. Okay. So yesterday, what we have discussed. First, about different types of mathematical model development of some process, such as liquid level system, temperature control system. Okay, so we have developed the model with the help of first principle of thermodynamics using the mass conservation, using the heat transfer energy balance, using the component balance. Okay, so based on that, we have understand the what the difference between the open loop system and the feedback system. And then we have discussed the feed forward control system and feedback system. Okay. Then we have discussed some questions why the process industries are important. And in order to that, we have discussed the problems regarding the operation control for the process industries. Okay. And which we have discussed the heat transfer and mass transfer like problems. And then we have seen the transients, and we have discussed the different types of process model. Okay. And then we have discussed the model part. Then we have discussed the different types of, the modeling equation. Which type of equations are usually occurred or usually developed in the mathematics for the model or system model. The system model consists of generally algebraic model, ODE, PDE. Okay, and the combination of maybe the combination of OD, maybe the combination of PD, and maybe the combination of all threes. Okay, so then we have discussed the types of different, the model in the terms of linearity and non-linearity. Okay, then we have discussed static dynamic system. In the dynamic system, we have discussed uh, the can say accumulation term. Okay, we have discussed the d by dt in the dynamic term equal zero. Then we have discussed the learned parameter, distributed parameter, and we have solved one example using the distributed parameters of the solid, the heat conduction in the solid. And then we have discussed the different types of model using the white box, gray box, and black box. We have seen the regulator sort of problem also. Then we have discussed yesterday the transfer function. Okay, the concept of transfer function. What is the meaning? What is the real meaning of transfer function? And then we have developed some equation of some electrical system, then the mechanical system, and then I have given one example. I have given one assignment, but due to the unavailability of the PPT, have not solved. I know, but try to solve today. I will give this PPT to all of you. So try to solve this puzzle. Then we have discussed that first order transfer function. Okay, of the liquid level tank, then linearization techniques. Okay, we will discuss in more these things after some times. Okay. Then we have discussed the distributed parameter model, that is the heat conduction of solid, and then we have concluded at the the state space equation, how the state space equation has been written for the your mass balance spring system. Okay, so I am starting with again with this PPT. Okay, so in a state space equation, what we have learned in the spring equation, spring mass damper system, the mechanic, which is basically a mechanical system, right? And the mechanical system, when we write the equation for this system, so force acting on the mass is ma, and that is the m into d2x by dt square, and whatever the force acting on the spring, that is the kx, and the damper force is bv, damping coefficient into the velocity, and that velocity is written in the form of dx by dt. Okay, so here the displacement is written in the form of the displacement is written here in the form of the y. However, the force is acting in the term of u. So when you written the equation is rearranged after the writing, then this is written. And when you multiply this one, it is when you this multiply, then this becomes ma, then becomes f into divided by dt. No? Uh, and then this is the damping. That is the f is here the damping force. Generally, the in the book, generally B is written. We have used the symbol FV. Okay, there is no problem. Both are the same. However, the key is the Hooke's constant, that is the spring constant, the k into x. Okay, so this is the basically force. Okay, this is the input. Okay, so against the input, the output is basically the displacement. Okay, so how it is developed? See, we have already discussed x1. I have discussed this is the x1 dot and x2 dot. That is a missing. So x1 is written here writing, and x2 dot is equals to y2 dot. So this the equation becomes like this: x1 equals to x2 dot. Okay, x1 dot is equals to x2. Our x2 dot is equals to this one. Okay, right. So we can develop this equation. So the more important thing is this equation: x dot is equals to a x t plus b u t and y is equals to cx t plus dut, right? So when you generalize the state space equation, I'm not going to details of it because this will be teach in the class and taught in the class. Okay, your teacher will be teach in the class. So I will taking just the overview only, so so that we can cover more and more topics that is not usually covered in the class. Okay, so that more aspects of the control system that will not covered in the class. Okay, so x1 dot is equals to fx1, this one. This is a generalized equation, whereas the x1 is the state variable and u is the input. Okay, and similarly for here and similarly for the n variable. Okay, so when you written in the this is the vector form. So x is a vector and it comprises of x1 to xn, where x is the x1 to xn, u is the u1 to m. Okay, so when how it is written, the matrix equation, it is written x1 dot is equals to what, a11. You can see from here, you can see here x1 is equals to what, a11 plus x1 but, and similarly we can write here. So is it, I think it is no problem. X1 dot is equals to a11 into x1, a12 into x2, a13 into x13, and so on, a1 into x1, right? Similarly we can write the all the equation this one. Okay, that is the your state equation. So finally, the compact equation we can write like this: x1 dot is equals to x plus b is equals to cx. Okay. So now see the, I will try to develop one. I will give one example of the process industry problems so that you can understand how the state space equation is developed. Okay. So now see, this is the one very classical example used in the process industries. This is the only the two tanks, the interconnection of two tanks, but there is a one the beauty of this connection, the see the first this connection and one other connection in this one. Okay, so see any do you find any difference in between the two tank system? Wait for a minute. Wait for a minute. Wait for a minute, so that you can understand it easily. Okay, so now see, have any difference between this you know this one and this one? Obviously, yes. The interconnection of the these two tanks and these two tanks are entirely different, and therefore the characteristics and the response of the system becomes entirely different. Okay, so this connection, basically, this connection is known as the non-interacting type connection, whereas this type of connection is known as interacting system. Why it is called non-interacting? Because when the output, the product of the first tank is when entering into second tank is not connected directly, but it is going through via the air. This is going through the air. However, this is going under the pipe, and this is interconnected to each other. So resistance of this R1 and the relation of this R1 with this one are entirely different. It will take the different equation, and therefore I am saying the the response will difference. So what happened? See, the we have to develop the we're trying to develop the model of this non-interactive system first. So you have already seen the development of the first order single tank system, single tank problem. So what we have written, basically this is the problem of mass transfer. Q is nothing, Q is your volumetric flow rate, and that is a meter cube per second. So meter cube per second, and the density is mass upon volume. So the basically this one is the rho into rho into q. So this is mass upon volume, that is a kg per meter cube, है ना? And then q is equals to, so this will cancel to each other and becomes a meter cube per second, right? So therefore, I have taken this one only, q minus q1 a dh1 by dt. You can refer the previous model, okay. And similarly for the tank two, is it totally independent, okay. The flow rate entering into the second tank is nothing but the q1, and the product is coming from q2. So we have written in minus out q1 minus q2 as equals to whatever the accumulation will occur in the tank 2, that is the A2 to ds2 by dt. So this one and this one is a totally independent equation. And as we know, if the valve is shows the linear characteristic R1, if R1 shows the linear characteristic, if the linear, then then what we have to do, we have to the equation the equation is written as q1 equals to h1 by r1. However, when you write the equation for this one, so you can write the q2 is equals to h2 by r2, and this equation is only valid for the linear system, okay. So just put this value q1 equals to this here and q2 is equals to here, and solve two equation. After the solving the equation, already what happened of the first system. The q1s, what is the q1? This q1s, whatever the output flow rate, and what is the whatever the input is q. So the transfer function, I am repeating once again the relationship between the product and output upon input in Laplace transform. Generally, we have taken and putting all the initial condition zero. Okay, so we have already discussed why the initial condition zero, why we have taken the Laplace transform. Okay, so that the need of the system. Okay, we are just due to the need of the system, we have taken the Laplace transform. We can take the J transform. We have to basically establish the relationship between the output upon input. Okay, so therefore we have taken. Okay, so now however, the q1s upon qs becomes 1 upon tau 1s. There's no problem, and we have already solved h1s upon qs as equals to r1 upon tau 1s plus 1. In the previous slide we have already discussed. So h2s, what is the h2s upon q1s? H2s upon qs means H2S upon QS, H2S upon Q1S becomes, as similarly, H1S upon Q1S becomes R1 upon 1 per tau 1S. However, H2S upon Q1S, that is the level output upon input of the flow, is relation is making the relationship like R2 upon R2 upon tau 2S plus 1. So just to put all this to solve this equation, and you got whatever the output is finally S2, the level of the tank. We have to control the level of tank 2 with the input first entering feed flow. Okay, so QS, that is the QS. So ultimately, the relationship Q2S H2S upon QS it becomes R2 upon 1 plus tau 1S into 1 upon tau 2S. So you can see here this one is nothing but a second order system. Second order system. How this is a second order system? When you multiply this one, then it becomes tau 1 tau 2 s square plus tau 2s plus tau 1s plus 1. Okay, and when we take the when you solve, then it becomes R2 upon R2 upon tau 1 into tau 2 s square and plus what becomes tau 1s plus tau 1s plus tau 2s, right? And the plus 1. So this is your final equation becomes, and this is the standard equation of the any terms of the any second order system. Now the time now we time for some simulation. Okay, so see, now, I want to discuss here what the response time, response system, response of the two tank system. So once we said this is your basically one single tank system. This is a single tank system, and when it comprises with the two tank, then it becomes a double tank system. So when we compare the response of the one tank and two tank, then obviously one tank system is faster. The response of the first single one tank system is faster than that from the second one. Okay, than the two tank system. Okay, so how it is? How can we find the response? How we can find the response? So in the MATLAB there is a you can write your code. Otherwise, you have to a Simulink model also. With the help of Simulink model, you can find the response of the system. Suppose this is the queue. This is the step response. Step response. We will discuss what is the meaning of the step. Now, just to see what is the step. Leave that. What is the step? So just we have applying some staircase of input. Okay, the staircase of input with the, let's say, the unit is with the magnitude 1. Okay, and this is in the MATLAB there's a just to put the value okay of the transfer function. Let's say this tau 1 is the first time constant of the tank is 0.5, and the second is, let's say, 1. Okay, and when you simulated the system, obviously this is an open loop system. We have not used any controller. Similarly, this is the single tank system for the, this is the first tank. Okay, this is when we take the single tank system and then compare the response of the system here. Okay, with on the screen. So this the output will come here. So you can see this is the one tank system response. This is this one, and this is the obviously second two tank system response. So when we compare the response of these two systems, you can observe that the response of the second two tank system are obviously slow than the single tank system, and it quite be obvious. So when you increase the number of the tank, then the response will reduce as shown in this figure. Okay, you can see here. You can also find the response of the system. How the response of the system is found. You have taken only one. You have taken only one. Uh, you have taken only one tank, then the other tank, then the other tank, and the time constant of all the tank is, let's say, 1. So 1 upon tau s plus 1 upon tau s plus 1 upon tau s plus 1. When it is combined, then it becomes the response like this. When it is single, then the response is like this. Okay. When it is two, then the response is like this. Okay. And then it is three, then response is like then. Okay, and then it is 4, then the response level like that. So you, as you can visualize here, as the number of the tank is increases, the response of the system decreases, right? Now come to the interacting system. Now other connection, other interconnection, other arrangement of the connecting the tank two tank system is obviously this one also. So in this system, the output of the first tank is going to enter into the second tank with the help of some pipe. Okay, this is the pipe, and we are sending this using this one. Okay, so this connection is basically known as interacting system. And what happened basically, the flow rate is here Q1, let's say. Okay, and this is the entering into the second tank. So so once we what is the equation for the tank one? So Q minus Q1, Q in minus out is equals to whatever the accumulation is to the tank. Obviously, for the second tank, Q1 is entering and Q2 is out. So we are writing in minus out whatever the accumulation into tank. Okay. Now the relationship between the R1. The relationship of R1. What is R? Since R1 is a linear, but it it is dependent on this height also and this height also now. Okay, I'm repeating once again. This R1 is basically linear in both the cases. We have taken same, and this R1 is basically dependent on the this is the function. This is the function of H1 as well as H2. H1 as well as H2. As H2 or H1 will change, the resistance of that valve also will change. So the relationship is established like this: Q1. Okay, this Q1 basically this Q here in the previous we have written only Q1 and Q1 is equals to H by R. Q is equals to H by R. But here we have written Q1 is H1 minus H2. H1 minus H2. Whatever this H1 minus H2 divided by R1. So this is the relation. And however here there is no problem in this equation. Again here it becomes simply Q2 is equals to S2 by R2. This is no problem in this equation. Okay. So now similarly just putting the solution, putting these values into this equation and try to solve, and you have your final target is to find S2S upon QS. S2S upon QS, and obviously when you solve, then you got the such type of real output, that the R2 upon tau 1 is tau 1 into tau 2 s square plus tau 1 tau 2 A2 into R2 s plus 1. So what is the difference in between them? What is the difference between them? When you multiply this equation, we only got R2 upon what? Tau 1 upon tau 1 tau 2 tau 1 tau 2 plus tau 2 tau 1 tau 2 s square plus tau 1 plus tau 2, okay, and then into s plus that is the 1. But in this case, plus a1 r1 plus a1 r1 is one, the one a1 r2 is a star. So due to this we have to the response of the both of the system is entirely changed. Okay, so now your target is to this is the time of again puzzle. So you have to solve this question. You have to develop this model and try to find out the transfer function S3S. Okay, S3 up S upon QS. Try to solve this transfer function. So this is your one of the assignment problem. Try to solve. Okay, if you develop such type of if you practice such type of problem, then you can solve any type of model. Okay, usually used in the process industries. Right. So now see, just I want to develop the same model using the status space techniques. So what is the benefit of the status space techniques when we convert the same model into the status space? Okay, the here we have written the model into the Laplace transform. We have established the transfer function in the form of Laplace transform. You can find here, and same equation may be written in the form of status space. So what is the need of that status space equation? We have already discussed that the status space equation is applicable for the non-linear system also. However, the transfer function is not available for the non-linear system. Also, the transfer function application is simply not applicable to the MIMO system, that is the multi-input and multi-output. However, that is only restricted to the single input, single output. However, here this is applicable for the multi input and multi output variable system. Okay, and one of the greatest advantage of using the status space technique is we have written the equation in the form of some matrix, and the MATLAB or whatever the computer simulation generally use the matrix multiplication, matrix addition, sub type of matrix application. Therefore, we are using this. It is easy for the simulation. It is easy for the computation using the computer. So therefore, we are representing our problems, our models into the status space technique, status space equation. Okay. One of the greatest, advantage that is and that I have discussed the non-linearity, because most of the problems of the real-time problem are the non-linear, and we are restricted towards the linear system, LTI system. Okay. So, however, our course is very basic, and we are not going to the details of linearity, non-linearity. However, I will try to solve one or two example of non-linear, how to handle the non-linear system that we have discussed earlier from using tank system. But we will take again that problem so that you can understand it very clearly. Okay. So see, this one is the tank. Okay. Again, this is the non-interacting tank, and in this problem, the U1 is entering U1 basically in the state space. In a state space, generally U is written for the input. However, X is written for the state. Here, the U1 and U2 is nothing but your flow rate. Okay. So U1 and U2 are the two flow rate, and Q1 is also one flow rate that is entering into the tank 2. So in the tank 2, U2 and Q1 is entering. However, the in tank 1, U1 is entering, and from tank 2, the Q1 is going to out, and similarly for the Q2 is from the tank 2. So when we write the equation around the tank 1, you can simply write U1 minus Q1, U1 minus Q1 is equals to whatever the accumulation inside the tank, A1 into dH1 by dt. And Q1 is nothing, H1 by R1. So therefore, we have written using the linear relationship of this one. Similarly, you can write the equation around the tank 2. So you can write the tank 2 what? U2, okay, Q2 plus Q1 minus Q2 is equals to whatever the accumulation into A2 ds2 by dt. So U2 plus Q1, and Q1 is written in the form of H1 by R1. However, Q2 is written in the form of H2 by R2. These two equations, this one is the first is the A1 dH1 by dt, U1 minus H1 R1. A2 is equals to dH2 by dt, U2 plus H1 by R1 minus H2 by R2. So when A1 is taking this side, okay, right side, so the equation becomes like this. And similarly, the second equation may be written like this. Okay, so this is the first order differential equation basically, and the H1 is now H1 dot. Okay, so H1 dot is written like H1 dot is written like minus of A1 R1 minus of A1 R1 into H1, right? And S2 dot is equals to we can write minus of minus of R1 A2, 1 upon R1 A2 into H1, 1 upon R1 into H1, and minus of this one into S2. Okay. And what about the input? Input dH1 by dt, H1 dot is equals to this is already calculated, this is already calculated. Now, okay. So now this one dH1 by dt is equals to what? Minus of R1 A1 into H1. H1 dot is equals to minus 1 by R1 A1 into H1 plus 1 upon A1, 1 upon A U1. Right? Similarly, here we have written for this one U2. Okay. So that this matrix is nothing but the X dot matrix. This is nothing but the A matrix. Okay. This matrix is nothing but the X matrix. This is nothing but the B matrix, and there's nothing but the P. So therefore, we can write all the models in all the process models in the terms of a status space equation using the x dot is equals to ax plus bu. And what is the output? Output is what? What is the output? Y output is nothing but the y is equals to if the output y is to be level in the tank 2. So if the output is like this, y is equals to ch, y is equals to nothing but ch. So what is this one? Y1 is equals to 0 into h1, and what is the output is of this tank. We have to ultimately control this level S2. So simply you have written what? Y is equals to simply S2. Y is equals to S2, right? So this one is the equation. So y is equals to nothing but y is equals to, we can write here C C into X, okay, plus somewhere we have written D U, okay. Generally D matrix is 0, D matrix is 0, but this is the ultimate final format. This is the final format for the the equation. equation. Okay, sorry for the interruption. Done. Wait for a minute. Wait. Sorry. Is my voice audible? Is it fine, Amitesh? Is it fine? I think
Yes, sir.
it is going smoothly. Yeah. Okay. So okay. So this is the final, basically the format: x dot h equals to x plus bu, y is equals to cx plus du. And yesterday we have already discussed why we have written the title ABCD. ABCD of process dynamics. So basically the state what you have taught in the what you have studied we will studying in the class, that will be the basic of control system, that will uh, the third year. But once you got the knowledge of the basics of the control system, and you entered into the higher study of the control system, then you encountered only with the state space equation. Okay, so from the state space equation, the control system, the real control system will start. Okay, so there's no problem. So now see, this is the now coming. We are entering into the world of the transient traces. Now we are entering into the transient traces, basically time domain analysis. Okay, so in the time domain analysis, the response of dynamic system is to an input is expressed as a function of time. Basically, we want to now find out the transient of the system. Okay, after after applying some input, such as here. See, you can see here. Uh, See from this system. Let's say this is the transfer function. Now this is the flow rate. Okay, and this one is the basically the change in the level of the second tank system. So when we change the input in the tank one, then the level of the tank two will change accordingly. So the getting the some saturation for the S2, it will take some time. So during that time, how much it will take for the saturation, for the settling, we have to analyze. So for the analysis of that, we have to supply some input, and we have to check what happens with the output. Okay, so for that purpose, we want to study the time domain analysis. Okay, so it is possible to compute the time response of the system if the nature of input, and it means we have to first determine the nature of the input. Okay, what we are supplying as the input, and second, the mathematical model of the system. So I think we have already we are enough. We are very enough to understand what is the how the
Power off.
how the mathematical model of the system are developed.
Power on. Barry.
So how the mathematical model of systems are going to develop, we have already discussed. Okay, so now usually the input signal to control system are not known fully ahead of time. So the problem is the real time system is the input system is the inputs what we are going to apply to the input is not known. Basically, the nature of this input is exactly what we are going to supply is not known. Okay, how the input is going to change, we don't know. Okay, so but we are just taking the the some classical uh, testing signal we are applying, so that we can test the output with the response to the input. Okay, so it is very difficult to express the actual input signal mathematically by simple equations. However, we have developed some relationship of that input. Okay, so the characteristic of the actual input signals are sudden, how the input are changing. So the question is this one. Okay, so we just analyze the different nature of the input, and then we have tried to mimic that or try to develop such type of input in the terms of mathematics. Okay, so as we already know the developed mathematical model, and once we able to find out the input, then we just applying into the that transfer function or that model, and just visualize the response, open loop response. Okay, so that we have already seen in the the model, second coupled model, coupled tank system. Okay, that they're interacting or non-interacting types. So the input, the general nature of the input is like sudden shock. Sudden shock means, let's say at t equal to 0, in very short time, in a very short time, the magnitude of the the input or the value is very 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 high at t equal to 0, then it is like a shock. ऐसे भी कर सकते हो तुम लोग कि मान लो कि तुम्हारे टीचर अब तो कोई मारता मारता पिटता नहीं है क्लास में, लेकिन लेट से अगर टी इक्वल टू 0 पे अगर तुमको अचानक से कोई बहुत तेज कोई थप्पड़ मार दे, है ना, या तुमको कोई सडनली तुम बिना बताए चोट लग जाए, तो बिल्कुल बेहोश टाइप का जो हो जाता है, उसको हम लोग टी इक्वल टू 0 पे एक सडन शॉक कहते हैं. ओके, you don't know what happened in the very small time. A very high input, a very high input you will apply, that is, project like mathematics, a sudden shock. Okay, second is sudden change. Sudden change you can represent like this. This in input is like t before t equal to 0. Before t equal to 0, the input was, so let's say 0, and t equal to 0 suddenly it was changed to the 1. Okay, so this type of the input is used in the testing the control system. And second, the constant velocity, that is ramp type of system is we are using. Okay, this is the ramp system. And then the constant acceleration, that is the parabolic type of the input is we are using. So this basically important input are sudden shock and sudden change. However, these are important but not much more important. Okay, our focus is only for to the sudden shock and sudden change. So the dynamic behavior of a system is therefore judged and compared under the application of this signal, this test, this input signal. Or this input signal is known as impulse. This is the impulse signal. This is the step signal. This is the ramp signal. However, this is the parabolic. Okay, this is the ramp signal. This is the ramp signal. This is the parabolic. Okay, parabolic. Okay, and then this is the this is impulse. Impulse means it is a very high value at the in very small time, and this is the step input. Okay, so this is the like this. Okay, now the other standard signals of great importance is sinusoidal. So sinusoidal signal is also one of the input we are applying, but I have not included in this. This is a very important, but I have not included in this PPT. This is that's the sign T. So I will try to give one example using the sinusoidal, so you can visualize the problems very easily. Why we are using such type of sinusoidal input? Okay. Now the other standard signal is yeah. Okay. Now come to the mathematics of this test. So it is very basic signals you have already studied, I think, in the signal system. If you don't know this, it is my duty to just introduce this signal. So this one is impulse signal. At t equal to 0, the value is very high. However, this is the mathematical. If you studied in the signal system, then this is represented by -1 by a. This is 1 by a. The concept is like this one. Okay, and the magnitude is, I think, sorry, sorry. Okay, so this is minus a by 2. Okay, and this one is a by 2. Okay, and then 1 by the magnitude of this one is a, 1 by a. Now what is the concept here? The concept is, listen very carefully, it is very important for your for your engineering problems, because you are electrical engineers, so you have to know this, you should to know this one. What is this? Okay, so as you decrease this, what we have to do, basically the area of this region, the area of this uh, pulse signal is fixed. That is the one. Okay, so we have to fix this one and change the width. So what we have to do, ultimately, if we want to change the area, if we want to keep the area one, and let's say this is approaching in this side and this approaching in this side, then we have to increase this value. Agree? So we have to increase this value in order to make the area one, as we have decreased, we have reduced this width. Okay, so after, if it will approaches t equal t towards zero. Okay, if we are approaching towards zero, this line, this point, then it means the magnitude becomes very very high. So if it becomes tending towards zero, then it tending towards infinity. Okay, so is it clear? To I think it is clear. If it tending towards zero, then it should be tending towards infinity for making the area one. Okay, so this is the concept. This is the concept of the the step impulse signal. Okay, okay, so this one is basically the concept of this one, a step sorry, impulse signal. So delta t is basically defined a at t equal to 0, and t equal to not equal to 0, the value is 0. However, the this is also defined like this one. Delta t is nothing but the value is infinite. Okay, infinite at t equal to 0. However, the value is 0 at t is not equal to 0, right? So this is also one definition. This is the, this is the unit impulse becomes a, and if it is not defined, then it is impulse signal, right? So okay. Now the step signal. The step signal is what I have changed. This is the change in the input, as from the before zero, the value was zero, and suddenly the t equal to zero, the output is changed at one. But such type of this is only mathematics, but never be the ideal. This system is never be you can realized. Okay, because it is a non-causal system, and the amplitude, you when you read the signal system, then will got the, once there is a phenomena, Gibbs phenomena, and using the Gibbs phenomena, if I ask a one question, that's a very popular question: what is the value at before zero, before t equal 0, the value is 0, no problem. Before t less than 0, the value is 0, no problem. And then greater than 0, the value is also a, no problem. But what is the value at t equal to 0? What is the value of t equal to? Mathematically it is written a, but exactly it is either 0 or 1 a, you can't say anything. Okay, because this is the discontinuous. This is a discontinuous at t equal to 0. At t equal to 0, t equal to 0, the function is discontinuous. Okay, and the function, since the function is discontinuous, you can't be able to find the value. Okay, so according to the Gibbs phenomena, the we are taking the average value. So the actual value at t equal to 0 is a by 2, average value, average of this one and this one. Okay, average value we are taking, but for the mathematical for the mathematical convenience, we have taken this value one. Okay, so ut is equals to nothing. Ut is equals to a and 0. So this is the definition of the step input, right? So ramp signal. Okay, what is the ramp signal? Ramp signal is nothing but the t, which slope is one. Slope is anything 45-degree whatever, and the equation is t. Okay, for the t greater than 0, and the value is 0 for less than 0. Okay, so this is the ramp signal. Okay, now come to the parabolic signal. The parabolic signal is nothing but the at square by 2. For the t greater than 0 and less than 0, the value is 0. Now, so this is the the conclusion what we have studied: impulse signal, step signal, ramp signal, and parabolic signal. Now there's a relation between, now we want to develop the relation. Let's say integrate the del t equal to 0. At t equal to 0, this value is, let's say, a. Okay, and this is that from t equal to 0 to, let's say, t equal to infinite. Okay, or now we are going to integrate this value, 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 this value at the continuous point. So what we got? We got like the equation like this one. Okay, we like got the picture like this one, and this is the basically integration. So when we integrate del t, then you got ut, and when you then what is the integration of a dt? So when you integrate this one, then you got simply at. Okay, sorry, you got 80, and when you integrate this one, you got this one. Similarly, just to take the differentiation, once we take the differentiation of this one, then you got the relation rt, and when you differentiate rt means 80. When you do the d by dt of 80, just to got a. Okay, so this is the step signal, and when you integrate the step signal, so as we have discussed already, this is a t equal to step signal, this one, or t less than 0, the value is 0. However, the t is greater than 1, for t greater than 0, the value is amplitude is a. Let's say here a. Now differentiate this one. Since the function is continuous at t equal to 0, so before t equal to 0, we can differentiate. So we got here the 0. Okay. However, when differentiate this one, we got the 0. So what we ultimate, the remaining portion is at t equal to 0, this portion, and this portion is nothing but, you can know, this is the a. So when you differentiate the step signal, you just to get the impulse signal. Okay, so it is a very basic things you have to know, and I know this will be obviously covered in your class also. So now come to the Laplace transform. How to you calculate the Laplace? So Laplace is nothing. Laplace transform of ft. L of ft is nothing but the integration of 0 to infinite ft into e to the power minus st dt, right? E to the power minus st dt. So this is the formula. So now just we are when we use the impulse input. Okay, when we take the 0 to infinite a into e to the power minus st. Okay, e to the power minus st dt. So using the properties, one, there is a property, here it is at t equal to 0, then we have to put the value at t equal to 0 and find the value a into e to the power 0, that is the 1. Okay, this is the property for the the function of the impulse signal. Okay, so must you read in the signal system. So the Laplace of the conclusion is final conclusion. The Laplace transform. If you not don't, if it is not, I think it is not understand clear to all of you. But try to read these things in the literature or the books. Okay, so Laplace transform of this one, Laplace transform of the impulse signal is nothing but the same value a. Okay. However, if you are taking the Laplace transform of ut, that is a, then just to when you take the Laplace transform, then it will come to the a by s. Okay. And what about the ramp signal? You can find out the ramp signal. There is no problem to find out this, and same for the parabolic function. Okay, so now come to the response of the system. This is a very important. Okay. So now time response to dynamic system. Dynamic system is, what is the meaning of dynamic system? The meaning of dynamic system is nothing but these comprises of differential equation, first order differential equation generally. So all the control system we have seen already. The system is either the first order system or the second order system. Based on that, the response is comes. So see, this is the you know step signal, and when we apply to the system, then system responding. and system respond like this one. Okay, system respond like this one. So this is the time domain analysis. When you're changing the when you're supplying some input with variation of time, then you got some output with variation of time also. Now this is there are two types of basically the analysis of the control system. First is the time domain analysis. Okay, time response as we have written. Second, the frequency response. When we apply some frequency input, okay, then as we got responded to that the frequency response. Okay, we have not included in the present course the frequency response. However, uh, for the analysis of tuning in the PID control, we will use Ziegler-Nicholas method. At that time, we will try to cover 1 to 2 points for the Bode plot techniques. In the Bode plot techniques, we will find the gain margin and phase margin. Again, crossover frequency and the phase crossover frequency. And with the help of that frequency, with the help of that margin, we will able to find the tuned parameters of the PID controllers. Okay, so we'll see there. But majorly, I have not included the frequency analysis because due to the lack of due to the we can't be able to complete all these topics in 3 days. Okay, so we are taking only the overview or the major topics of the control system here. Okay, so you can okay. Now time response of the system has two components. Basically, first is a transient response. This is the steady state. Second is the steady state response. So we have already seen from the tank system and from the operating process problems. First, the steady state problems and the transient problem also. Okay, so So when the input is applied to the system, as the input is applied to the system, at that time, at the same time, the output will not change. It will take some time. Okay, and after that, sometimes it will take to settle the output or come to the steady state. It will take some times. Okay, so that time is basically your transient period. Okay, that time is your transient period, and as a control engineers you don't want any tangents. Okay, you don't want any tangents, so target is to maintain or use set point as soon as possible or the desired value as soon as possible. Okay, without wasting the time. Okay, so we have our ultimate target is to remove this one. Okay, so when the response of the system is changed from equilibrium, it will take some time to settle down, and this is called tangent. Okay, so as you know, this is applied input and it will take some time to go there, and once it is achieved, this is settled. There's no problem. So but we have to achieve this value as soon as possible. Okay, so this is our target. Okay, so the response of the system after the tangent, the response of the system after tangent is called the steady state response. Okay, so this is the steady state response and this is the tangent response. This is the tangent response, this side is the steady state response. So tangent response depends on the system poles only. It means uh, for the analysis of the system, basically it is not only the poles, basically it is a closed loop poles. Closed loop poles. In gate, one problem will comes generally one problem has been asked, I think in 2007 or 8, I don't know the exact date. The problem was 1 upon s plus 1, and the question is the transfer function gs is given, I think. Okay, okay, no, it is given like it is given like it is given like transfer function. The transfer function of any system is given by 1 upon s plus 1. So your target is to find the type of the system and the order of the system, right? Type and order. You have to evaluate or you have to compute the type and order of the system. So Remember always, it is very important concept and always be asked in the gate examination. uh, the type of the system is used for the steady state analysis, right? Steady state always I have not covered here yet. It is I am just introducing to you. This is used for the state space, or steady state, sorry, steady state, not space, steady state. This is the state, okay, steady state. And the order of the system is used for the analysis of the tangent, okay. So now the type of the system will defined for the open loop system. Second important thing, it is the open loop system. However, it is defined for the closed loop system. It is defined for the closed loop system, okay. So what is the problem? Once we are saying this is a type, so what is the type? You don't know the it is either the open loop system or the closed loop system. It is the open loop system or a closed loop system. You can say the order of the system is one. The order of the system is one. However, the type of the system is your open loop state, and define the open loop system. What is the type? Basically, what is the type? You have to know the number of, it is defined as the number of open loop poles. The number of open loop pole. The number of open loop poles. Open loop poles lying at origin. Lying at origin, okay, lie at origin, so this is your basically the definition of the type of the system. The type of the system is only defined for the open loop system, and it is the open loop pole lying at the origin. So here we can see here the s to the power is 0, and s plus 1 is written here, okay. So it is looks like the sir s power 0 is here, s power 0 is there. So 0 type system is this one. This is the type 0 and order 1. What is the order? Order is the maximum power of the polynomials. You can say the maximum degree of this polynomial. The power of s is maximum power is 1. So this is the your order is 1. Okay. Okay. So number of poles, it will define the maximum number of poles of the closure system. Order of the system is number of poles of the closed loop system. And I'm repeating once again, the type of the system is the number of open loop poles lie at the origin. Is it okay? So for this problem, for particularly this problem, when you're talking about this one, sorry, okay, 1/s+1, okay, 1/s+1. This is a problem. So there's a, it means the number of open loop pole is 0, but the transfer function, it is written here transfer function. So transfer function, it means transfer function doesn't means it is open loop or the closed loop. It is not the given, but generally the transfer function is used for the closed loop system, not for the open loop system, okay. The transfer function for the closed loop system is defined as gs upon 1 plus gshs, 1 plus gs upon 1 plus gsh is the standard equation we have seen yesterday, okay. So gs is the your forward path gain, whereas this one is the feedback we have already discussed yesterday. This is the comparator, okay. And with the help of this error is generated, and this is the input, and this is the output, right? So this is the transfer function gs upon 1 plus gshs. So with the help of this is the open loop. And what is the open loop transfer function? Open loop transfer function is nothing but the gs or gshs. If the unity feedback is this one, if the unity feedback this one, this is 1, and this is also 1. So this is the transfer function for the open loop system. So now this is given, gs upon 1 plus gs is 1 upon s plus 1 is given. It means in the question it is given gs upon 1 plus gs. Basically, this is the closed loop system. Okay. The transfer function, when nothing is written in the problem, it means it is generally we have considering the problem is of the closed loop system. So the transfer function of the closed loop system is given here 1 upon s plus 1, and this is the closed loop system. Okay. Now we have to convert this closed loop system into the open loop transfer function GS, so we can find out. Okay. Let's say this value is x. So with the help of this, you can calculate this. So when you solve, you got 1 upon s, I think, something like that. Okay. So you can solve. So ultimately, final answer is the type of the system and order of the system of this problem is basically one. Okay, the type is also one, order is also one. Here, however, from the problems, it is looking like this is the output. The type is zero. Okay, so I think it is clear to this one, all of you. So the transient response depends upon the system poles only and not on the type of input. Okay. It is therefore sufficient to analyze the transient response using step input. The steady response depends on the system dynamics and the input quantity. Which I will discuss. It is then examined. Then now see, this is a first order system, and there is a one pole at what is the location of the pole? S is equals to minus one upon t. S is equals to minus one upon t. Okay, so the gain of the system is k. However, the time constant of the system is capital T. Okay, so this is the first order system. Now we will start with the input. We are taking the step response. Generally, we are taking the two types of input: delta T, that's the impulse response, and ut, that is the step response, as we have discussed in a few minutes back. Okay, so DC of the gain system is ratio between the, what is the gain? DC gain. The DC gain, it is one question has been asked also in the GATE problem in 2007, 8, 9, 10. I don't know the exact year, but the question has been asked. What the DC gain? What the DC gain transfer function was given, and that have asked the DC gain of the system. So the DC gain of the system, the ratio between the input signal and the steady state value. Okay, steady state value. So let's say this is the problem, the GS upon 3s plus 1. So now the tau is 3s 3 second, and where is the DC gain is 10. That's no problem. For the following system, for the following, so what is the gain and DC gain and constant? So S plus 5 is given. You can take the 5 common. Okay, this is the S plus 5 becomes, okay, and 3 by 5. So the DC constant is this one, and the time constant is this one. These are problems. Okay, now see the impulse response of the system. Impulse response of the first order system. So what is the what is the impulse response of the first order system? Let's say we have taken the impulse response. Sorry, impulse input delta t, and the Laplace transform of delta t is one. Delta t is one. So as we have discussed, delta t is equals to a at t equal to 0. The Laplace transform of this one is again a. So if the input is 1, the Laplace transform of this one is also 1, right? So this is the unit impulse signal. Unit impulse signal. We have discussed earlier. Okay. So once we supply the unit impulse input 1 as the input, then after this calculation, we have to find the CS. Okay. So you have to remember one things. The multiplication in time domain is always equal to the convolution in frequency domain, and vice versa. And the convolution in time domain is equal to multiplication in frequency domain. Okay. So here the response is nothing but the multiplication of the two signals. Okay, this one. But in the time domain, it is the convolution. The output is the convolution of two signals. However, in the Laplace transform, when it is going, Laplace is basically frequency domain. It is a multiplied. Okay. So now see how it is calculated. So CS is equals to what? K upon TS plus 1 when the input is 1. Okay. Now calculate the Laplace inverse Laplace of this equation. So when you rearrange this equation like this one, and then we take the Laplace inverse of this, then we got the Ct is equals to kt k upon t e to the power minus t by t. And when you plot this equation, simply you can find like this one. Okay, so this is k by t. It is minus t by t. Now, when you take the step input instead of the Laplace impulse input, just to take the step input. We already said the input variation in input is like you know a certain shock or certain change. So we have tested the certain certain shock here just by the impulse input. Sorry, impulse input. Uh, However, here we have we have checked with the tried the response with the help of the step response. So step response is applied. So this is 1/s. Okay, if the cs is multiplication of this quantity with this quantity in the Laplace in the frequency domain. However, when you taking that in the time domain, it will be the the convolution. So this is the case when you multiply this one, and when you take the inverse Laplace, okay, impulse Laplace, then you got the equation Ct equals to this one. No problem in this one. Okay, so when you plot this one, is a very important curve. See, this is the curve will come after the plotting this value. Okay, now see. So this is we have taken the input set t a and the step input. The value of step input we have taken, let's say the ut is 1 here. If you take the input ut is equals to 10, if you take the in ut is equals to 10, this is sorry yt, sorry, the total dc gain is let's say 10. Okay, this is a 10. Okay, y is equals to this k. Okay, so the 63% of the final value is this one. Okay, and mapping this value corresponding to that time. Okay, this time is basically known as time constant. Okay, so what is the time constant? Time constant decide the basically the speed of the response of the system. And basically this speed how the speed will decide the time constant. With the help of the time constant is fast. If the time constant is slow, we will see the effect of that time constant on the system. Okay, so 1 upon tau s plus 1, you can check how it will affect the systems. Okay, so basically what is that, how is it defined? 63% of the final value at the correspond to that time is nothing but the uh, uh, the tau time constant. Okay, now see here what happened at first time t. The 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 response will achieve the response will basically the equation, the response is ct is equals to k e to the power minus t by t. That is if you write ct is equals to, if the k is 1, if k is we considered 1. Okay, and we have written the equation. Hey, in this plot the k is we have taken 10. However, in this plot we have taken the k is equals to 1. Okay, so once we plot, this type of plot will come. We'll take the response in this one. Okay, now the value of t is varying. Okay, now put the value t is this small t. When just put the value t is equals to a small capital T here, and that will cancel to each other. Then it becomes 1 minus e to the power minus 1. Okay, and you calculate this value, this will come to this one. Okay, just put t is equals to capital 2t. Okay, and then you will see the when you put t is equals to capital 2t, 1 minus e to the power minus 2, it will comes 86.2. It means for the second time the response will achieve up to this point, and third time if the response will achieve at this point 95%. 95% will achieve in third time. 98.98% will achieve in the four time. Okay, it means the response will going to settle. The response, the final response is going to settle in the 4T or the 5T. There's a no change in the 4T and 5T. Approximately, it is the same. 98.98%, 99% is approximately is it is a comparable value. So we have said after the 40 after the 40 the response will achieve the steady state. The response will achieved the response has been achieved to the steady state. Okay, now you can see here the response we have promised to. So this is the response. You can see how the response will changes with respect to when you changing the time constant. So as the time constant increases, t is equals to 1, t is equals to 3, t is equals to 5, t is equals to 7. See the response. You can see. Sorry, you can see here. This is the response is very fast when you taking the time constant is minimum. Time constant is low. It means what? What to conclude it? Our target is to achieve this steady state as soon as possible. It means we have to make the time constant very small as soon in the limit you can say also in the constant also in the allowed value. Okay, minimum is doesn't mean 0 0 points or something. It becomes a minimum. It should to be minimum, but in the limit, in the constant, in our satisfying all the conditions of our parameters. Okay, now see. uh Now we have here it is a variation the t. Now we are varying with t is a constant. Now we are varying t is equals to we have considered 1 and taking the gain varying. Okay, when the gain is k is equals to 1 and k is equals to 10, k is equals to 5, k is equals to 6, k is equals to 1. The the set point, it will change the set point, uplifting or downlifting the amplitude of the system. Okay. Now the practical determination of the transfer function of the first order system. So now, in generally, in when you encounter the problem of Ziegler-Nicholas or the Cohen-Kuhn method for the tuning of the PID controller, we will see tomorrow. In that such type of problems, basically the response, basically in the industry, I'm giving one. I'm try to illustrate the simple things from the example. Suppose we have to control some things, control some parameters, temperature or level or the flow of any process. Okay. So ultimately, first you see the visualize the open loop response of that system, and then only you are able to apply some control. Let's say you have applied some PID control with some PID control with some settings. Okay, and after that settings you got some response, but you just find out the whatever the response has been occurred after the tuning, that is not very satisfactory. So again your target is to manipulate that tuning settings or the parameter settings of the controller, and then so that you will achieve a very satisfactory response. Ultimately, until unless you not will not get the satisfactory response, you will try to change that parameter settings. Okay. So now, for that purpose, you have to visualize the first order response of that system, the response of the systems. Okay. So in order to that the response of the system was given for your problems. Okay. Now visualizing or analyzing that response, and you have to change the parameter settings. So first of all, you have to calculate the mathematical model using that visualization. Okay. So ultimate conclusion is this one. My conclusion is this one. I want to say these things. You have to calculate, you have to compute the mathematical model with the help of the response. Whatever the response has been occurred, with the help of that response, you have to try, you have to find out the develop the model. Okay, so see the one example I have taken one example, okay, so that you can understand here. See, I have taken this example from the Seaborg book, Process Dynamics and Control, and this is the problem. See, sorry. So 7.4 shows the response of the temperature T in the continuous stir tank reactor to a step change in the feed flow rate W from 120 to 125 kg per minute. Amitesh, we have time now. We can continue for the 5 minutes or 10 minutes. Amitesh, Amitesh, can you hear me? Hello, hello,
Hello,
Amitesh,
Matthias?
Mr. Anis,
Anis,
are you hearing me?
are you hearing me?
Mr. Anis,
Mr. Anis?
or
Or
Yes, sir, I'm here.
okay, okay.
okay, okay.
So we have time, 5 minutes or
So we
10
have
minutes.
time,
We
5
can
minutes or 10
continue.
minutes. We can continue.
Yes, sir, sure, sir.
Okay. So I will
Okay.
take 5 to 10
So I will
minutes.
take
Then we
5 to
will
10
start
minutes. Then we will
tomorrow.
start
Okay. I
tomorrow.
will take only
Okay.
5 to 10
I will
minutes
take only
to
5 to 10
cover.
minutes to
Okay.
cover.
Okay. Okay. So is my
So
presentation is visible
presentation is
to all of you?
visible?
Okay. Okay. So now problem, I want to discuss one problem so that you can understand mathematical model, how the mathematical model can be developed with the help of the response of the system. Let's say this is the response of any temperature control system of the steer tank problem. Okay, this is the step change response we have got. This is the step change. So the flow rate changing from 120 to 125, 120 to 125 kg per minute. Okay, this is the change in the flow rate. We are changing the flow rate from 120 kg per minute to 125 kg per minute. The response of the system will change from 140 to 160 like this one. Okay, there's no problem. I think the response will come like this. Okay, now our target is to design or develop the approximate first order model for the process and find out the condition. Okay, so this is the problem. So this problem is taken from the Seaborg. Okay, so solution is like this. So what is the change in output? Okay. Sorry, input. So change in input is basically 125 to 120, 120 to 125. That is the change in 5 unit. Okay, so 125 unit has 5 unit has been changed of the flow rate. However, the output changed is 160 to 140. Okay. So the steady state gain is defined change in output upon change in input. So change in output is 20 degrees and the temperature is changing from 160 to 140 and the input flow rate is changed from 125 to 120. So this is a 4 degrees Celsius per kg per minute. So this is K. So any transfer function, the first order transfer function is defined as K upon 1 per tau s or tau s plus 1. So you have evaluated the value of k. Now your target is to find the value of tau. And you know what is the tau? Tau is basically 63.2%. So you can from the figure this is the tau is given already. This tau is already given. So just to this is the 63.2%. Okay. So 63.2% value is this one of this tau at this value. Okay, or otherwise you if it is not given, just to check or just to find out the using the some statistical tools, you can find this value. Okay, at what time at this value 63%, 63.2%, what is the ultimate this will correspond, and you can evaluate this value. Okay, so here it is given already, so no problem in that. So 5 minute is given. So and k is also given. So you can find out the transfer function tau 4 upon 5s plus 1. However, the final value. final value means what is the value this t infinite, what the value t infinite. So you can find out the t infinite like this. The 140 temperature is starting one from the 140 we have started. Okay, and then it is 63.2% into 20. 20 means we have changed total changing the 20. So it will multiplied and added with this one. That this is 152.6. So at the 63.2%, at the 63.2%, this value has been come. Okay. So I think there is no problem in that. Okay. You can compute like this also. You can find out the transfer function like this also. Okay. So this is the problem. Now come to the first order system with a zero. So as you know, this will represent the denominator will represent the whole and it will represent the zero. Okay. So if the transfer function, how why such type of equation will be written, I will discuss tomorrow because due to some problem of the controller, we are realizing the control the form of some filter. Okay, using generally the derivative kick. One concept of the derivative kick will be discussed tomorrow. Okay, so in that kick, we will introduce such type of value. Okay, we will see tomorrow. Okay, now let's say this such type of model, such type of first order model encountered with you, and you have supplied some 1/s type of input, that is the step input, and want to compute the response of the system. Then you can if you then just to multiply the 1/s into this value and compute the Laplace inverse, and you such type of you in response will you got. Okay, now there is a one such type of delay system. What is the meaning of delay system first to see? However, first I tell you what is the delay system. I will show you after this slide. But generally, you remember that you always remember that e to the power minus std, e to the power minus e to the power minus td or ts. This is the transfer function for the any delay system. Okay, so suppose this the delay system is first order delay system is like this one. And the response of delay system is this such type of response will come. Okay, so now what is the meaning of lag? What is the meaning of delay system? What is the meaning of delay system? It means you see here. Let's say I'm visualizing you with this one example. I'm illustrating with one example. Let's say this is the tube. Let's say this is a one tube. We're supplying some feed here. We are supplying some feed here and taking the output from this side. Okay, as a Q. So this Q is entering here at let's say t equal to 0. But at the same time you are not able to get same value at yt. So yt will take some time. Yt will take some time to give the value q. It means at t equal 0 you have applied some input, but t equal to but t equal to tau, let's say, it will gives the response. It will the response will got at this time. Okay, then similar with this one. So what is this? This time is nothing but the delay time. Or what the delay time? Delay time is means suppose volumetric flow rate is nothing but meter cube per second. You know, meter cube per second. What is the volume? Volume is nothing but the meter cube. So volume of the volume of the tube when divided by the volumetric flow rate, it will nothing but meter cube cancel and second will come. And this one is the delay system. Okay, so the tau is nothing but the A into L, that is the volume, and that is the volumetric flow rate. So for any time, any pipe for the pipe system, it is nothing the AL upon Q. Now see what is the transfer function of such system. So Yt is equals to what? Yt we will come xt minus tau. Why? Because this Yt what is this? How is it be written? Yt is equals to x of t minus of tau. You can write this one with the help of signal. We are already studying the signal system. What is the Laplace of this one? The Laplace of this one is e to the power minus s tau into we have taken xs, right? So ys becomes e to the power minus tau s into xs, right? Now the this is the output and this is the input. We're taking the relationship between the output upon input, and it will come e to the power minus s tau. That is demonstrated here. That is demonstrated here, e to the power minus s tau. Okay. Okay. Now come to the some approximated value. Sometime it is not generally written e to the power minus s tau. Okay. Or okay. E to the power minus tau s is maybe written like 1 upon tau s, and 1 e to the power x, e to the power x is generally written 1 plus x square upon factorial 2 and so on. So this is the equation. Now if we retain, if we approximated this equation up to the first value, because this value is very, if the tau is very, it can be neglected. Okay. So e to the power minus tau s becomes 1 upon 1 plus tau s. Okay. One method of writing it means e to the power minus tau s is approximated upon 1 plus tau s. This is the one method. Other method is writing like this one, e to the power minus tau s, e to the power minus tau s may be written as the half portion is written here e to the power minus tau s by 2, and the half portion e to the power tau s by 2. Okay. And expanding in this one up to the first term, and this equation, thus this approximation is also known as first order paired. However, if you will take the second order term, then it is known as second order paired. It is very, very important for the process engineers, for the process control engineers, to consider the delayed response. Okay. Delayed response. So this is the second order system. Now we will discuss because the time is not relying, it is going very fast. So I think it will remains. So we can continue tomorrow. Hello.
Hello? Yes, sir. Sir, query for today has been shared on your email.
So can we stop here?
Yes, sir. The query for today has been shared on your email.
Okay. Second order system we will start from tomorrow, and then we will try to PID controller. If Mitesh,
Yes, sir.
if you allow to take one more days, then we can continue. We can
Okay,
if
sir.
uh, so just to talk with your principal and your higher authority,
Sir,
so that we
I will
can
ensure that the permission is granted tomorrow.
uh, because the topic is more clear to the students. Otherwise, some things will missed. Okay,
Okay, sir.
so I am just checking the response. Okay, so first, is it my audible? If I say audible, hello everyone. Is my message audible?
Yes, sir.
Okay. So the first question asked from the one students is problem in the time response of the system. So just want to what is the problem in time of response? Basically, there are so many problems encountered with the problems in the time response, because time response, the calculation with the time response is not very easy, and uh, especially when the system is higher order, and it is very easy to handle with the frequency domain, frequency analysis. Okay, so if we will if the time will allow, I will see from one to two problems. uh, you can if you will allow, I will solve from one example. Okay, so that you can understood it uh, very easily. So see here, I am just presenting the presentation again. So okay, is the presentation is visible to all of you?
Yes, sir. Visible.
Okay. So see, I'm just giving one example so that you can understand it. Let's say this is the 1 upon s plus 1 transfer function is given. Okay, 1 upon s plus 1 is given, and the problem is asked, it is the sine t response. It is very easy to calculate the response with the help of ut and rt, that is the unit step and delta t. But when it is said the response is like the input is like this sine t, that is sinusoidal, that is I asked illustrated in the previous slide. So when you supplied some sine t, and the question is that find the response of the system here. The response of the system is calculated. So the one method is to convert the sine t is equals to 1 upon s square plus 1, there's the Laplace, and then you multiply this one and then got the inverse Laplace. And ultimately, this question again asked in the GATE exam in 2009 or 10. I don't know the exact 12 or 14. I don't know the exact date, exact year. But so this problem has been asked already. So 1 upon s square plus 1 this is not very good approach to solve such type of problems. There is a method to solve using the frequency domain analysis. So using the frequency domain analysis, you can find the solution of the response of the system is very fast. So the magnitude is one, and the omega is, that is the frequency of the system is one. So, as you know, the input, when the inputs is in sinusoidal, the response is always sinusoidal. The only change in either the magnitude will change or the phase shift will change or some damping will come in the picture like this one, okay, or the equation becomes this ones, okay. So, however, if you see here, sorry, if you see here, if you see in this case here, let's say sine t is applying here as an input, okay. So in the magnitude is one, the frequency is one, so output is again this one. So change in only the magnitude and the response, and the magnitude is here. You can write s equals to j omega, and omega square plus 1 is the input. So, and the phase angle is, you can calculate omega upon tan inverse omega, I think minus of tan inverse omega, right? Minus of tan inverse omega. This we'll discuss tomorrow. So the magnitude when you put that, only 1 by root 2 will come, and this is the minus 45 degree. So the final response is 1 by root 2 sorry, 1 upon sine, okay, sine t minus 45 degree. This is the answer of of this problem, okay. So you can calculate like this one of such problems, right? So second question you have asked, second query is again explain about the standard stress signal. Just just to try to read, okay. If the topic is not clear, then you can again ping me, okay, you can call me, no problem. This topic will cover, I have showed you this topic must be covered with from your faculty, okay. So this is no problem in that, okay. And signal system faculty and the control system faculty both are the teaching the same topics in introduction, okay. So please suggest a few books of the control system. There are so many control system books are available. In respect of the, if you want to study the control system only, then the best book is I.A. Nagarat, M. Gopal, and B.C. Co. And Indian book authors, one of the Indian book authors is also available. There is B.P. Rathi. However, the process for the process dynamics, I would suggest the three books. First is the Kufner, process dynamics, and second book is the Seaborg, that is the process dynamics and control. And for the development of model using the data is the one book is available in the market from IIT Madras faculty, system identification, that is written by Arun Tangirala, Professor Arun Tangirala, IIT Madras. Okay, these are some books available in the market. You can, if you don't have that book, I can provide, I can say on some the same soft copy for to the your faculty, Amitesh. And then, sir, please explain the working of servo motor. It is now open loop or closed loop system. So servo motor we have discussed already to yesterday, that servo, that is set point is fixed and the load changes. Okay. So, however, the concept, if you want to discuss, we will see. We'll discuss tomorrow. Servo motor, okay, that how the transfer function of servo motor will, okay, or derived. We will, if you allow, if you say, then I will discuss tomorrow or coming days. So I have a confusion for a very long time. The value of the step signal is equal to zero, is a or a by two. Sir, we consider the juice phenomena, then it is definitely a by two. But sir, in many books it is given, or in the PPT it was given a for t equal to 0. So in exam, what value? Okay, this is not confusing, students. At the see the case is, if you applying the Gibbs phenomena, then basically at t equal to 0 the function is discontinuous. Okay, the function is not continuous. So you must to apply the Gibbs phenomena for that, and Gibbs phenomena is only saying you have to take the average value. So it means you have to take the a by 2. No problem in that. But for the mathematical sake, for the mathematical convenience, you have to take the value at that discontinuous function, the maximum value a. Okay, it is only for the mathematical convenience or for the mathematical solution, shape. Okay, so whenever you handling with the control problem or singular problems, just to take a at that point only, a. Okay, if someone is asking at t what is the value at t equal to 0 exactly, then you tell that value. Okay, so how to check if the system is stable, or just by looking the graph? Oh, oh, see, we have not discussed the stability. Basically, if the pole, the one concept is very simple concept. If the pole is lying in the left hand side, then your system will stable. Tomorrow we will try to discuss some stability criteria, so that we can cover these things. Okay, for the second order system and the stability criteria we will try to cover tomorrow, and then day after tomorrow we will try to cover the PID control, design of PID control, if this will allowed. Okay, so in the process industry system, do we use a standard form like data input system? It is a very good question we have asked, how the process industry will handle with some type of delta function or the ramp function or the step function. So see, suppose we have to apply the impulse function in the terms of flow rate. Okay, so what we have to do? We have to do at a very small time span. You have to drop the water, a very drop to water, a very large amount. Okay, a large amount of water should be poured in the systems or top to the systems. Okay, so it will like a t equals 0, the very value high value. This is basically a practical problems, practical things. Okay, particularly the very high amplitude will represent only represent the delta signals. Okay, suppose the flow rate is 10,000, and we're just changing 10,000 to 20,000. It will take some time, but this is the steps input. It will considered to be a step input. Okay, so such type of a mechanism will adopted for the changing the input in the process industry. Okay, if the transient response is not present in the system, then what happens? Obviously, transient will be the problem. If the transient is not problem, then the system is ideal. Okay, so we are studying the control system. We are only studying the control system to removing the transient. If the transient will not occur, then your system is fine, no problem. Okay. If the transient response used for the stabilization of the system, obviously we will see tomorrow how the stabilization, how the stability will come in the picture. If in the system the post is not present, what happen? They're not possible. System transfer function without the pole, the transfer function is not defined. If the system is not present, if the feedback is not present in the system, then tangent is not work or not. See, feedback basically for the open loop system we have listed earlier in yesterday lecture also. Uh, if your open the system is open loop. It means you have assumed whatever you are getting, yeah, the 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 the, the result is fruitful. The result is fruity. It means your result, whatever you got, is assumed to be stable. No harms in that. But as you applying the feedback system, it means some tangent will come, because you are adjusting the input and output mapping. Okay, and in order to that mapping, we are not getting the output same as the desired value. Okay, so as in order to find the desired value, you have to do some adjustment. Okay, and for that, you are changing or tuning some parameters also always. Okay, the feedback is not present, the system is done. So for the open up system, there is no tangent. If the tangent is only introduced when your feedback system is. How can I use neural network to control knowledge system in a simulator? See, it is a very good question you have asked. I have tried. I will I have dropped one slide or two slide using the regression and the data development, model development using the regression techniques. But as you know, this is the third year students in the course, so I have not included this things. But if you say I will give one or two example with the help of neural network and regression model, so that you can understand how the how the mathematical model can be developed with the help of the data. That is very very important. This is a very very important question. It is a actually this is the real question. Okay, the real problem is only nowadays we have how do we handle the data, how we have developed a model with the help of the data. So therefore I am saying one book is available. If I will not discuss, then one book is available for that system identification by Arun Tangirala. This is a very very introductory book, and you can understood each and everything with the help of the NPTEL lecture is also available of that guys. Is very very good lecture. That lecture is very fine. How unity feedback system are type zero system? We have already discussed. We already discussed. So why unity feedback is useful? Why not? See, for the it is the unity feedback is fixed. The feedback is fixed one for only for the instrumentation problems, because if the dynamics of what is the feedback system, feedback we are just using only the measurement system sensor, or the some transducer introduced. Okay, so using that transducer or sensor, your target is to only the measuring. So you only want to handle with the process dynamics, not with the dynamics of the measurement system. So we are considering our whatever the measurement system has been used for the measuring the physical quantity. That physical quantity is linear relationship. Okay, first linear relation. If your measurement system will show the non-linear, then it will create a problems. Okay, so we have to develop the first order model, second order model, third order model. We want to develop, we are considering our measurement system is showing the zero type model. Okay, sorry, first one like a linear model. Okay, so I'm just forgetting what I want to say. That the feed that okay. Next problem is why unity feedback useful. I have already told. Please explain briefly in control system criteria. Okay, so I always confuse in the stability and the stabilization. The stability we will discuss tomorrow. Then there is no confusion between stability and stabilization. Both are the approximately stability is same thing in expression. No problem. How to get DC gain from a transfer function? I already told. You can uh, a steady state insignificant pole from the signal. Zero order one, which is better type of the system, either first order or second order. You can't say on comment on the on which type system is good. It depends on the process. It depends on the process which which type of process you have considered, either the first order system or the second order system. That you can only say the response of which response is good, either the first response, okay, in the term of the performance parameters only you can say, okay. So I think all the query I have been addressed, okay. So if you are not satisfied with any answer, just to drop a mail. I will try to solve your problems, or you can call me separately. So I will discuss tomorrow. If you timed allowed, then I will try to discuss one example of servo motor, okay, and then the neural network problems also, and a regression model, okay. So it is very important to have asked a very good question in this query, okay. So thank you, audience. Let's handle session is handled to Amitesh. Amitesh, please.
Yes, sir. Yes, sir. Thank you very much for today's session, sir.
Mm,
We will continue tomorrow
mm.
at the same
So
time.
okay, so, if you take the permission, then we can continue from day after tomorrow also, so
Yes,
that the
sir.
students can get benefited. Okay.
Yes, sir. I will try to take the approval from the authorities.
Thank you, Amitesh,
Thank,
and thank you
thank you
everyone.
very much.
Stay tuned, and I will share the PPT today. Okay. So thank you very much.
Yes,
Okay.
thank you, sir.